doing trigonometric derivatives or going backwards and doing antiderivatives. What's that? Right, yeah, once you integrate, you've used up the integral symbol to actually integrate, so you drop the integral and the dx together. Okay? Then we'll kind of talk about in calculus how the dx is actually the chain rule that jumps out, but it actually jumps back in. Okay.
Is the mathematical term for antiderivative integration, or is it?
They're both okay. They're both okay.
Is that even like a mathematical?
They're both. Yeah, that's a good question. It's not a Mr. Wadeism this time.
Okay, yeah.
Yeah. The antiderivative actually is a word to say don't put the plus c, and then integration is the word to say do put the plus c. So they're essentially the same thing.
Yeah.
Yeah. Okay. But good question. Yes. All right. Yes, son.
What are we supposed to be doing in like curriculum?
Oh, we've already done the whole thing except for.
Oh, so you just kind of like we did all this stuff.
We went through it so fast.
I know.
Standards, so we're plugging along through the curriculum. We're already past it. So if you want to go back and review, you can go with that. All right. Anyways, now the last test, though, the last test is like some things we have to do on calculator. We're going to bring it back and show you how to type in a couple of things that are like awful decimals, really nasty decimals and stuff like that. So anyway, we're saving that. Okay. Now the next one. Notice that we have an integral symbol here. What's that question?
So for this one, would you have to put like a negative cosine?
That is a good question, actually.
Because it would have to cancel out in order for it to be a positive in this equation.
Right. You need something whose derivative gets you back to the question, right?
Right.
When you check it. So the only thing we did this year whose derivative is positive sine was negative cosine. So you're absolutely correct. Okay? So the derivative of negative cosine is positive sine. That works. And at the very end, you put a plus c right there. Okay? So if you see the integral, just do the antiderivative or integration, basically. That's it. Okay. Pretty easy, right?
Yeah.
Not bad. Okay. Now here's one way you can remember this, by the way. Did you notice that when we had cosine previously, didn't cosine stay the same sign?
Yeah.
When we went back? Okay, think about this. We're in opposite world here. Back when we took the derivative of cosine, what was the derivative of cosine every time we did it? Negative sign. So the antiderivative is positive sign. See how it's opposite now? Right? Every time we did the derivative of sine of x, what is it always?
Negative cosine.
The derivative of sine is cosine. So the antiderivative of sine is negative, so it's opposite. Okay? So you always check that in your brain and think, okay, wait, sine to cosine, okay, sine to negative cosine. Okay? Just do the opposite. All right? Now, D. Ooh, look at this. Turning at the stakes a little bit. Now you can use any variable you want. I'll tell you what, with trigonometry, a lot of times you'll see sine of theta d theta. Remember theta, right? The most popular ones in calculus that we'll use for integration would be x and u. These are really fun. There's a reason for that, but we'll discuss that next year. Okay? So, secant squared of u du. So it's like secant squared of x dx, basically. What if we did a derivative this year that turned out to be secant squared?
Tangent.
You know what? Tangent's derivative is secant squared. So it must be tangent of u plus c. There you go. How about that? Okay.
You're less going to be short.
Go through now.
All right, thank you.
And we're back. Okay, so on this problem here, now we have a what type of function? That is an exponential function, all right? Well, guess what? If we have all these rules for taking derivatives, I'm sure everything has a way to get its antiderivative somehow, right? Okay? Although there's some awful functions where you can't possibly go back and actually get its integration. We'll never see those, but there's some really nasty. Okay? That is the one difference, though. When you do a derivative, you can pretty much take the derivative of anything, right? No matter what I give you guys, you can use one of our rules and you can get to the derivative. But when you do the integration, it has to be in a very specific form. That's one of the tricks in calculus that we'll do, is how to get it in a simple form, because you can't do it in a more complicated form. Okay? So you can actually pretty easily make up something that you can't possibly integrate. So this one, though, this is a nice one. Okay? If you took the derivative of an exponential, how do we take the derivative of an exponential? It's the same. That's only the base. And then chain rule. Okay. If you do opposite world, you keep it the same, but instead of multiplying by the natural number, you divide by what in this problem?
ln of 3.
Natural log of 3. And you also divide by the chain rule, but the chain rule of A is just 1, so don't worry about it. That's it. That's easy. Okay? Let's see. So now we're dividing by natural logs instead of multiplying. That's it. So just think opposite every time you do these. Okay? And sure enough, if you did this derivative back the other way, that's just a number, so it would just carry along for the ride. This would kick out a natural log 3 that would cancel, and you get it. It would actually work. How about that?
It was 2A, would it be?
Divide by 2 natural log 3. Divide by the chain. Yep. There we go. Can do some of those in the future. Okay. All right. So we've done just about everything at this point. We've done how to get back from sine, cosine, secant squared, exponentials, polynomials. The one that I'm avoiding, if you've noticed, there's one other type of function that we've not done here. You know what that is? Got sine, got cosine, got secant squared, exponentials, polynomials.
Natural logs.
So anyway, natural logs. That's the one major function we haven't done yet. Okay?
Keeps these so hard to set up.
Okay? This is a tricky one right here. Okay? You won't do that in pre-cal. We'll probably only do it in BC calculus because it's a really tricky one. You think it'd be simple? It's not. Okay? It's hard to find a function whose derivative ends up being natural log. It's easy to take the derivative of natural log. It's just 1 over x. But to find somebody that ends up being natural log of x, not so easy.
Can you do it for us? We have time.
Oh no, we have so little time, actually.
Well,
Well,
17
go
minutes.
for it. Go for
Okay,
it.
maybe later I'll let you in a little secret, okay? But anyways, all right. So we won't do that, but I'll tell you one thing we've not integrated. We haven't done tangent yet. We did sine and cosine, but we have not integrated tangent yet. Okay? And it was x, yeah. All right? Now, unfortunately, some people get carried away. They're like, okay, the derivative of tangent is secant squared, so I guess the integration of tangent is also secant squared. No, it doesn't work backwards like that. Okay? We have to cleverly find some kind of function whose derivative just lands right into tangent of x.
Would you like to sign or cosine?
Kind of, yeah. Actually, you want a derivative that ends up being sine over cosine, because then that would be tangent. Very good, good thinking. Here's how you do it. Okay? That was good, though. That was pretty good. If you named it, I would have been really impressed. The integration of tangent, and this is one just to kind of memorize, is the natural log of the absolute value. And the reason you put the bar is you can only take the natural log of a what? Positive number, so that'll protect it for us. It turns out to be a natural log of secant of x. Interesting. Wouldn't guess that one unless you see it, right? And it's not secant squared, it's just secant. Okay? And then put the plus c at the end. Now there is one other acceptable answer for this too. Does anybody remember what the secant means? 1 over cosine. Okay? Which, yes, okay? If it's secant equals 1 over cosine, isn't that the same thing as cosine to the what power? Negative first, okay. Another acceptable form. If anybody likes this one better, and usually it's just like, you know, some people like this one better, some people like the other one better, whatever you like. This is okay too, negative natural log of cosine of x. Any idea why that's the same thing?
It's the exponential inverse power. Yeah.
If secant is cosine to the negative 1, only in natural log world can you kick the power out to the coefficient to the front, right? So it's actually the same thing. See that? Cosine to the negative 1, kick it out. There you go. Okay, very nice. So either one of those answers is acceptable right there. Now, you don't have to write anything else. You can just relax. Let Mr. Wade do all the work. Okay? Let me show you how nice it is that this derivative ends up to be tangent. Okay? Why is it the only function in the world that works perfectly? Okay? Watch the beauty of mathematics as it all unfolds before our very eyes. Okay? Because you actually know enough pre-calculus to do the derivative of this right here. You could have done it before. If you had to take the derivative of negative blah, 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 what does the negative do first? Okay. Carry along for the right, it's coefficient. Natural log derivative would be 1 over the base.
Yeah, you carry it.
Okay, and we can just drop the bar for this case. Times the chain rule of the inside, which is what?
Negative sign.
Negative
All
sine of
that
x.
cancel.
And you get plus sine over cosine. It's tangent, isn't that nice? Perfect. There you go. And the C just became 0. Okay. Pretty cool.
Shows
So you had to make it just right where, finagles its way to tangent.
I show it's law.
All right, fine. No pre-cal classes ever seen this before in the history of Page High School. Or probably the history of the world.
YouTube's about to.
Anyway, and now we'll go to blackout. All right, catchphrase. Okay.
Thank you, can you stop it?
Okay.
Thank you.
Oh, kids, we don't have time to do National Log of X today. Let's not do that at all. Okay.